Hey guys, Mr. Janowski here. Per that email that was sent out about what's going on with online learning for possibly the rest of the year, we'll see. That's going to keep getting updated. But anyhow, per that email, astronomy is now kind of an optional course. So I'm providing things that are, you know, optional, just for enrichment, just to keep you interested in this stuff. So I'm going to make some videos like this one where I kind of talk through the slides. So I've already put up the chapter 13 slides up on Google Classroom, and I'm going to start adding videos to this. So if you're still interested in astronomy, hopefully you are, you'll watch these videos, but you're not going to be graded on any of this stuff. So I don't know, good on you if you want to watch them. So let's get started. So this is chapter 13, measuring the properties of stars. So if you look at this picture, one of the stars in this picture is the star that is the absolute closest to the Earth, not counting the sun. So can you see it? Depending on how good your screen is, if you're looking on a phone or if you're looking on a laptop screen, you might notice this little guy here circled in red. So this guy is Proxima Centauri. Um, Proxima, same root, has proximity or approximate. It means close to. And Centauri, it's in the constellation of the Centaur. Yeah, that guy is about 4.24 light years away. So, yeah, still very far. What do we have here? About 25 trillion miles away. Million, billion, yeah, about 25 trillion miles away. 4.24 light years. In contrast, the sun is 8 light minutes away, or about 93 million miles away. So, yeah, Proxima Centauri, the closest star after the sun, and yet it's still really far away. So, if you compare that guy to this guy, Alpha Centauri, so the way they name stars, or at least one of the ways they name stars, is they go by the constellation. So the Centaur, Centauri, and they name the brightest one Alpha, and the next brightest one Beta, and then the next brightest one, which I don't know if is in this image, would be Gamma, uh, Delta, and so forth. But anyhow, this guy here, Alpha Centauri, it is only slightly further away. So Proxima Centauri is 4.24 light years. I think Alpha Centauri is like 4.3 light years. So it's only slightly further away. And yet you'll notice this one seems very, very bright. This one, we had to circle it in red so that you could find it. So why does this one seem so much brighter than this one if they're about the same distance away? And the answer is because Alpha Centauri actually is much more luminous. There's actually a difference between brighter or brightness and luminosity in this chapter. But yeah, this star looks brighter because it actually is of itself very much brighter. And this little point here, we call it Alpha Centauri. This is actually a binary star. It's two stars that are very close together, but they look like one, so sometimes we call it one, just one star. We'll get to binaries later in this chapter. So, if you are 1 AU away, so if you are as far from these stars as the Earth is from the Sun, Alpha Centauri would be about twice as bright as the Sun. So, yeah, it would be too hot for us; we would all die. But it would only look about twice as bright, so it wouldn't look that much crazier. However, if you were that same distance away from Proxima Centauri, it would only be less than a fifth of 1% as bright as the Sun, because this one actually is that much brighter. So if you were 1 AU from this guy, Beta Centauri, it wouldn't look 200% brighter than the sun. It would look 4 million percent brighter as the sun. So why does Beta Centauri, why does it look less bright in this photo if it's actually much, much brighter, more luminous than Alpha Centauri? And the answer is because it's actually much, much further away. So this guy is about 4 light years away. And this guy, who looks like, they're good buddies and they're right next to each other, is actually almost 100 times further away. So remember, when you're looking in a constellation, even if two stars look like they're right next to each other, right next to each other on the sky, you can't go by that. In this case, this one is actually much further away than this one. Oh, and Beta Centauri is actually a triple star, a trinary. Yeah, there are groups of stars. 3, 4, 5, and 6 stars are possible. So I'll put a link to this video in the description to my own video. Yeah, it's Hank from SciShow talking about could we visit other stars, which isn't exactly on topic, but he is talking about going to Alpha Centauri and Proxima Centauri, the nearest stars, and how much time it would actually take to do that, and how we're actually thinking of trying to get around that. So, interesting video. So, how do we measure the distance to stars? We use triangulation and parallax. We've already dealt with parallax. That's the thing where you hold your thumb out in front of your face and then you blink one side to the other. That's just a form of triangulation. So it's difficult to measure the distance to stars, but it's really important because if you know the distance, then you can start to figure out things like their mass, their radius, and their energy output, meaning how much light are they actually putting out. So there's lots of ways to do this that we'll get to later in this chapter. But if the star is nearby, relatively nearby, the way we usually do this is triangulation, in particular parallax. So how does this work? So in triangulation, the analogy they made in the book is you're standing on one side of this gulch, valley, whatever. There's a river running through here, and you want to know the distance to this tree. Well, you can't take a tape measure and walk there because there's a river between you and the tree. So what do? You line yourself up so that you're directly looking at the tree, and you want to know this distance, but you can't measure it directly. So what you do is you walk a little bit along this way. So you go here, some known distance that you can measure. And then you look back and you figure out, well, what's the new angle to the tree? Because I was all squared up to the tree when I was standing here. This was a right angle. If I walk 1, 2, 3, 4, 5 feet, 5 meters, I don't know what that's supposed to be, and then measure a different angle, you can do a little bit of trigonometry. If you know one of the angles and one of the sides of a right triangle, you can figure out all the other sides. So that's how you can get the distance using trig. See, there was a reason we taught you these things. So the main method of triangulation we'll use is parallax. So we've been doing this for a while. It is the change in an object's apparent position. So it's only an apparent change in position caused by a change in the observer's position. So nearby objects exhibit more parallax than more remote ones. So what this picture here and these guys are showing you is parallax in this star. So some of these stars are way, way far away, so far that you can't observe any parallax on them. But star A here is a relatively nearby star. So what you do is you make very precise measurements of that star's position in July compared to the background stars. So in July, I'm looking at this star, and it looks like it's right next to this guy here. And then you wait 6 months. And 6 months later, the Earth is on this side. So, we were 1 AU from the sun here, and now we're 1 AU from the sun on the other side. So, we're 2 AU away. And if we look back at the same star, parallax has occurred. So this guy is no longer right next to this guy. He's moved way over here. This, again, is the same thing as holding your thumb out in front of your face and then blinking back and forth. So, yeah, in this slide, I explained what I just explained on the last slide. So the closer a star is, the more parallax you're going to see, but it's important to recognize that the parallax for even the closest stars, even for Proxima Centauri and Alpha Centauri, is really, really small. We don't measure parallax in degrees. If you think about how small a degree is, there's 360 of them in a circle. So pinch your finger to see how big a degree is. We don't measure in degrees. We measure them in arc seconds. So what is an arc second? Well, a 60th of a degree is an arc minute. So arc minutes are already really tiny. And then a 60th of an arc minute is an arc second. So 1 arc second ends up being 1/3600th of a degree. So for convenience, we use, when we're doing parallax, we don't use our baseline as being the whole thing. of 2 and we don't measure the difference in this angle and this angle. Just convenience, convention. Excuse me. The convention is you just do the half angle. You're only measuring this angle compared to the right angle there. And the distance you use is called a parsec. This is what defines a parsec. So, if the thing is 1 arcsecond away, if the thing shows 1 arcsecond of parallax, it is a parsec away. And a parsec is a little more than 3 light years. Sometimes I think it would be nice if we just always did it the same way. Always used light years. But parsecs, for the people who measure this, this is called astrometry, not astronomy, astrometry, measuring these properties. They like to use parsecs, so we use parsecs. And it's abbreviated PC. So here's your formula for parsecs. That relates distance in parsecs and parallax in measured in arc seconds. So if you're looking at a star and you measure 0.25 arc seconds of parallax, how far away is that star in parsecs? So just take this formula down here and you're subbing in 0.25 for P. And when you do that, you get it's about 4 parsecs away. And a parsec being about 3¼ light years, that means that star is about 13 light years away. How about if the parallax you measure is 0.1 arc seconds? Well, you do the same formula, but instead of 0.25, you're going to put in 0.1, and that guy's going to end up being 10 parsecs away, so about 32 light years away. So it's all just simple trig, and we've known how this trigonometry works for a very long time. For millennia, we've understood trig. So it seems kind of simple. The drawing makes it look kind of simple, but actually measuring it and measuring it well enough is really, really difficult. So the first parallax was not measured until 1830. So if you remember all the stuff we did about the history of astronomy and why the ancient Greeks didn't think the Earth moved, and why people thought the Earth was at the center of the entire universe and that the sun went around the Earth and things like that, it's because they realized, well, if the Earth is moving, we should see parallax. And they looked for parallax. They didn't see any. So they concluded that the Earth isn't moving. Again, the Earth is moving. The problem is they had no idea that the stars were so very, very far away. And the parallax that they were trying to look for was way too small for them to measure. And too small for anyone to measure until our telescopes got good enough in about 1830. So here's Hipparchus. He'll come up later in the chapter with something called the magnitude system. Just a little bit more on how we measure stars. So we've got this satellite, Hipparchus. Actually, I'm sorry, it's not being used anymore. It had a 4-year mission ending in 1993. Hipparchus, nice backronym it's called when you do this. High precision parallax collecting satellite. It went up there, it measured parallax from more than 100,000 stars and was able to measure them up to 250 parsecs away. So if the star, again, the key idea here is if the star is relatively nearby, you can measure its distance using parallax. If it's more distant, you're going to have to use other methods. And we'll learn those methods later in this chapter. So, quick review. I learned something today. What did you learn today? If you're looking at this picture, what is this picture about? This picture is about triangulation. Parallax is a form of triangulation. It's basically trig, and we can use trig and the fact that the Earth goes around the sun to figure out the distance to at least the most nearby stars. So, second question. Nearby stars exhibit more or less parallax than more remote ones. The nearby stars will exhibit more parallax than the more remote ones. Again, for any star, it's going to be very, very tiny. But if the star is relatively nearby, it will be bigger than if the star is further away. And what formula relates parallax and distance in parsecs? It is distance in parsecs is equal to 1 over parallax in arc seconds. So that's what defines what a parsec is. Again, it's parallax. It's a form of triangulation. So that's the first part of the slides for chapter 13. Hopefully you found that interesting.